Right. So if you just look at the first question now for this particular year of your paper, which term represents a physical quantity? Now, when you're talking about physical quantity, what is actually a physical quantity? You learn in chapter 1 that physical quantity must have two things. It must have magnitude as well as unit. For something to be classified as a physical quantity, you must have both magnitude and unit. So now looking at the answer choices that you have here, if you look at the first answer choice, meter, this one is not a physical quantity. This one is actually unit of a physical quantity. Okay, it is the unit of a physical quantity. So A is automatically out. And then after that, when you look at the second answer choice, percentage uncertainty, let's just say, for example, maybe you have 37%. Now, from here, you can clearly see that, yes, there is magnitude. And is the percentage sign a unit? It's a bit ambiguous, right? So this part, we just leave it for a while. Well, what about for quark flavors? Now, quark flavors, you already learned from particle physics, you have up, down, charm, quarks, and so on and so forth, right? So when you're talking about quarks, quark flavors specifically, this one is also definitely going to be out. Because for quarks, if you're just talking about quark flavor, there's no magnitude involved. Neither is there any unit involved. So quark flavor is definitely out. Now, if you look at the last one for your question, you have spring constant. Now, spring constant could be something like this, where you have something 10 Newton per meter. Okay, this is spring constant, right? So notice that this one clearly has a unit, and it also sorry, this one is not unit. 10 is actually your magnitude. This one clearly has magnitude, and it also clearly has unit. Okay, so between B and D, B is a bit ambiguous because although we see that you could have magnitude, the percentage isn't really a unit here. Okay, so percentage uncertainty is not considered as your physical quantity. Instead, you will actually say that spring constant should be your physical quantity because you can clearly see that it has magnitude and units there. All right, so answer for this is actually D. Okay, now then if you move on to part 2, if you're okay with this, just let me clear all the writings here. Maybe I can just leave it here also, no worries. Now, for question 2, which two units are identical when expressed in terms of SI base units? So you want to see for the pair of units that have been written here, are they identical in terms of SI base units? All right. Now, but before we can go through that, let's just identify the SI base units for some of the units listed there. Now, if you're talking about units of joules, you see there's a joules there, right? Unit of joules is actually the unit of work done, which is actually the unit of the product of force times displacement, which in your case is kg meter per second squared times with meter, giving you kg meter squared second negative 2. And then after that, you look at Coulomb. Coulomb is actually the unit of charge. But if you want to express it in SI base unit, it should be the unit of product or current times time. Okay, Coulomb is actually not an SI base unit. It's an SI unit, but not SI base unit. Okay, the keyword here is base unit. All right, so you have to express Coulomb in terms of SI base unit. You can actually find it out from the product of current times time. Current is base quantity, time is base quantities. You get the units together, you will get the SI base units. So in your case, this one should actually be ampere second. Okay, so that's for that part. And then after that, there's also another different unit here called Newton, right? Just now I went for joules. Coulomb. There's another unit here called Newton. This one Newton, everyone knows what it is. So let me just write it here. You're talking about units of Newton is the unit of force, which is the unit of the product of mass times acceleration, which in your case will be kg meter per second squared, right? So now that you have some of the units there in SI-based units, let's just try and make a comparison. If you're talking about joules per coulomb, this would be equivalent to kg meter square second negative 2 times with ampere second power negative 1. So that you're going to get the answer is kg meter square ampere minus 1 second negative 3. So you can see from there, it is actually not the same with the other units listed here. The one that's different is that there's a negative 2 here, but this one is negative 3. So A is out. Then you move on to the second one, where it is joules second. Joules you already know is kg meter square second negative 2. Multiply with second, you will get kg meter square second negative 1. Now this one is the same as the other unit that has been given to you inside your question. You see, this one is matching exactly what you see here. Kg meter square second negative 1. So this one by right should be the answer, but you can actually double confirm with answer C and D. So let me just write out answer C and D here. If you're talking about Newton meter, it will be kg meter per second square multiply with meter again, giving you kg meter square second negative 2. So this one is clearly not the same as what you have here, because this one is power 2 for meter, but this is power minus 3. Sorry, this is power 3. Okay, so C is out. Then if you look at D, where you say it's Newton second, if 4 is Newton second, this one again is kg meter per second square times with second, you will get kg meter second negative 1. So this one, if you compare it with the units written here, this is also wrong, because this is negative 1, but this is negative 3. Okay, so answer is obviously going to be B here. All right. Now, if then you move on to question number 3. Okay. A value for the acceleration of free fall on Earth is given as 10 plus minus 2 meters per second squared. Now, which statement is correct? Okay, now for your current case here, when you're talking about precision and accuracy, you see the answer choices here are referring to precision and accuracy. You would have learned before this that accuracy has two meanings. Precision also has two meanings. So if you're talking about accuracy, the first meaning of accuracy was that it refers to how close the reading is to your true value. This is definition 1. Then the other definition of accuracy is referring to the percentage uncertainty of your measurement. Okay. Then if you move on to precision, precision also has two meanings for you. Precision, the first meaning is the smallest change that, smallest change that can be detected. It is supposed to be the smallest change that can be detected by your instrument. Okay. Smallest change that can be detected by your instrument. And then after that, the second one is degree or scatter of readings. Okay, so accuracy and precision each have two different meanings here. So which one actually applies to your current question here? Now, if you're talking about precision, you probably cannot use smallest change that can be detected by the instrument, because this particular question doesn't relate to any kind of measurement done by any particular instrument. So we cannot use the first definition of precision. Instead, we will use degree of scattering of readings. And then when it comes to accuracy, how close the reading is to the true value, as well as your percentage uncertainty. Percentage uncertainty here is probably not something that we will use. We try to use how close the reading is to the true value. Okay, so let's just imagine this. If I try to draw a few lines here representing certain values, I tell you that the value 10 is here. Then this one is 11, 12, 13, this is 9, 8, and 7. Okay. Now, if your value is listed as plus minus 2 meters per second squared, it could mean that your value is between 8 meters per second squared to 12 meters per second squared. Okay, this is the range of your values. So if you look at it this way now, if it's between 8 to 12, your scatter is actually from here to here. This one here represents your degree of scatter. Okay. Now, if you try to find the percentage scatter here and compare with your nominal value, this 10 here is what you call your nominal value, or some people call it the normal value, whichever it is now. All right. So if I try to find the percentage scatter here, now I know my value is from 8 to 12 here. My degree of scatter here, or in other words, my range here, is actually 4. 12 minus 8 gives me 4, right? So my percentage scatter here is 4 divided by 10, giving me 40% if I change it to percentage form. This one times 100% is 40%. So my percentage scatter here is 40%. This one is actually not precise, definitely. Okay. Then after that, if you try to evaluate the accuracy, now accuracy here, if you're talking about acceleration of free fall on the Earth, this one you already know from doing so many questions so far that acceleration of free fall, the true value is 9.81 meters per second squared. So let's just assume that the 9.81 meters per second squared is actually this 10 over here. Okay, if you round it up, it's going to give you 10, right? So let's just assume that our 9.81 is right over here. Okay, so from here, we know that our value can go plus 2 from 10 to end up at 12. It can also minus 2 from 10 to end up at 8. Okay, so right now, if we want to evaluate the accuracy, we want to see how far can our values actually lie from the true value. So in my case, I will actually take this. I will actually take the difference, the maximum difference that my value can end up with from my true value. So in my case, I can actually find out the percentage difference here as 2 times over the nominal value times 100% to get it in percentage form. This one is 20%. Okay. Now this one, relatively speaking, compared to this one is considered accurate lah. Okay. The answer here is actually the value is accurate but not precise. That is the answer for question 3 here. Okay. Under most normal circumstances, I would actually say the value is not accurate and the precision is not that. It's not precise, it's not accurate. But somehow or another, this particular question, they actually say it is accurate. This is the odd thing about this particular question here. Okay, we can clearly see it's not precise, but when it comes to whether it's or not, it's accurate or not, it's a bit ambiguous. All right. Because like, let's just say right now, you look at the percentage difference is 20%. For some people, it's actually not accurate at all. For them, 10% will be considered the limit. If it's below 10%, then it's accurate. But if it's more than 10%, it's not accurate. And then for some people, 20% is their limit. Below 20% is accurate. More than 20% is not accurate. So it actually varies. But for your particular question here, they somehow kind of establish that this is accurate. So there's no other way I can explain this, okay? It's a bit ambiguous, all right? The only way I can actually kind of say why is it accurate is if you compare this percentage difference with your percentage scatter, this value is very much lower than this. So it's considered to be accurate, okay? So this one is one odd question. Okay, so if this one is okay, then I move on to question 4. So let me just clear this thing up. Okay, now question 4. If you look at this particular question, they mentioned that 2 cables are attached to a bracket and exert forces as shown here. What are the magnitudes of the horizontal and vertical components of the resultant of the 2 forces? Okay. So magnitudes of horizontal and vertical components of the resultant of the 2 forces, what they're actually asking you to do here is to find out the sum of your horizontal forces as well as the sum of your vertical forces. That's what the statement there actually kind of meant. All right. So you want to find the sum of your horizontal force followed by the sum of your vertical force. Okay. Now, but before you can do that, you need to see that the forces here are actually at a certain angle with respect to some reference. The 15 Newton here is at 20 degrees to the horizontal. The 6 Newton here is at 40 degrees to the vertical. So you look at the 15 Newton force first, you know you can resolve this force like this and like this. You can resolve it into 2 perpendicular components like this. Okay, so what should be the horizontal and vertical component here? Now you have learned last time in trigonometry, if you're talking about cos theta or something, is usually adjacent over the hypotenuse. And then when you're talking about sine theta, it's usually the opposite side divided by your hypotenuse, isn't it? So the thing that I just want to point out here is this: when it's cos, you usually look at whether you have an adjacent side. When it's sine, you always look at whether you have an opposite side. Okay. So if you refer back to this question here, when you go and resolve the forces, you look at the blue colored force, the horizontal force here. Notice that that force is actually adjacent to your 20-degree angle. So if I want to write out the expression for the component, it's actually just 15 cos 20, simply because it's adjacent to my angle. Then the other force must therefore be sine, so it's 15 sine 20. Okay, just like that for this one. Then you move on to the next force, the 6 Newton force. Same thing as before, I can actually resolve this force into 2 perpendicular components, one that is horizontal like this, and then one that is vertical like this. Okay, for the horizontal component, is adjacent? No, it's not adjacent to any angle. It's actually the orange colored force here. The orange colored force here is adjacent to my 40-degree angle. So this one will be 6 cos 40. This one is 40, right? Yeah, it's 40. Okay. So that one is 6 cos 40. Then the other force, the horizontal component here, must therefore be 6 sine 40. Okay. So now you have all the forces. Now you then want to sum up the horizontal forces. You only be looking at 15 cos 20 and 6 sine 40. So let's assume that going rightwards is positive. So in your case, there's no negative. It will be 15 cos 20 plus with 6 sine 40, giving you some value of 18.0 if you round it out to 3 SF. Okay, this is 18.0 Newton. And then your sum of Fy, let's just assume that going upwards is positive. So in my case, this one would be 15 sine 20 minus 6 cos 40. So if 15 sine 20 minus with 6 cos 4t, you will get the answer as 0.534 Newton. Okay, so this is the horizontal, this is the vertical. In your case, your answer should likely be C. Okay, so that's for this particular answer here. Okay, then after that, you move on to question 5. The curved line PQR is the velocity time graph for a car starting from rest. What is the average acceleration of the car over the first 5 seconds? Okay, now there's something here you need to first single out. This one is asking you for average acceleration, not instantaneous acceleration. So what you learned last time was this. Let me just erase this. Sorry. In general, when you're talking about acceleration we know is rate of change of velocity, which is just delta V over delta T lah, which is in turn the gradient of your VT graph. Okay, but what I never really mentioned to you last time was this. If you're talking about instantaneous acceleration, let me just cancel this one off. If you're talking about instantaneous acceleration, which is usually at a point, you would take gradient of tangent at that point. You would take the gradient of tangent at that point. Okay, but when it comes to average acceleration, between 2 points, you won't take gradient of tangent at a particular point. You actually take the gradient between the 2 points. So in your case, your question is actually asking you average acceleration here. So this is your velocity time graph, like this, all right? So the 2 points you're interested in, because you're talking about average acceleration here, you're actually talking more about this case right now. You're not being asked about instantaneous acceleration. Instead, you're being asked average acceleration, which is between 2 points. In your case, the 2 points is actually the first 2 seconds. So in your case, you're interested in the average acceleration between P and Q. So in your case, if you want to find the average acceleration between these 2 points, you actually take the gradient between these 2 points, which is this line here. So the answer here is actually the gradient of the straight line PQ. All right, not the gradient of the tension at Q. This one is actually for instantaneous acceleration. Okay, so this one kind of relates to what you learned before for something else, the average speed and average velocity thingy. So let's just say, for example, I give you one example here. I have something that moves like this in a wavy path, like this. So I move from point A to point B here, okay? So here, in my case, I told you that my total distance move, this one is my total distance of say maybe 15 meters. And then after that, if I'm talking about my displacement from A to B, this one is probably my displacement. This is my total displacement. This one here is total displacement of say maybe 8 meters. So in your case here, if you are trying to find average speed, this one would be total distance divided by time taken. But if let's just say you're being asked to find the average velocity, this one will be total displacement divided by your time taken. Okay, so if let's just say in your case here, I want to kind of relate it to average acceleration, it could be something like this. Say for example, when the object was moving along the green path here, that I subsequently highlighted in orange, my velocity is continuously changing. Let's just say maybe at this point here, it was 10 meters per second. Suddenly this one here is 8 meters per second. Then right over here is 12 meters per second. And then this one suddenly become 18 meters per second. Then it dropped down to 15 meters per second. And then subsequently over here, it became 22 meters per second. So in my case here, I have something that still follows the same path, but the velocity keeps changing also along the path. So if I'm interested to find out the average acceleration between A and B, is somewhat similar to what I've just defined here. My average acceleration here will actually just be the change in velocity between the 2 points divided by your time taken. Okay. This one here is change in velocity. Okay. Let me just write it out better. Okay, this is change in velocity between 2 points over time taken, which in turn will give you gradient between 2 points now, if it is in the form of a graph. All right. Okay, so that is for this particular question. Then if you're okay with that, then I'll move on to question 6. So let me clear this thing off. Okay, so for question 6, this one is a ball is thrown horizontally with a speed of 10 meters per second above horizontal ground. The ball hits the ground after a time of 3 seconds. Air resistance is negligible here. What is the speed of the ball just before it hits the ground? Okay, so there are a few things here that you should kind of identify out first. Now, the moment they tell you air resistance is negligible, this automatically tells you this. Weight is the only force acting. From there, you tell you A is constant, and then A is equals to G. Okay, the moment you see air resistance is negligible for something that moves through the air, it already tells you weight is the only force acting. So from there, acceleration is constant, acceleration will always be equals to G. So you're trying to visualize what's happening right now. You are trying to project something away from a cliff horizontally. So say, for example, this is the ball that you threw, and then you projected it with a certain speed of 10 meters per second horizontally. Okay. So from what we know, if you project it like this horizontally, it will follow a curve path that looks like this now. Okay, it follows a curved path that looks like this, and then it will subsequently hit the ground. Okay, so for the case where air resistance is negligible, if air resistance is negligible, there are 2 things you will always be able to say from here. You will always have constant velocity horizontally, as well as constant acceleration vertically. Okay, these are the 2 things that should come to mind the moment you see air resistance is negligible too, in addition to what I just wrote here. Okay, so you will have constant velocity horizontally, you will have constant acceleration vertically. So in my case, if the object is being projected horizontally from the cliff and is moving like this here, I will always have 10 meters per second horizontally. This one will always be 10 meters per second right over here. Okay, but when it comes to your vertical velocity, because you're projected horizontally here, in your case, this one, your initial vertical velocity is 0, okay, right at this point. But as your object continues to move downwards, it will actually start to have an increase in velocity because your acceleration is directed downwards like this, okay? Your speed vertically is going to keep increasing to some value, all right? So what do you want to find from this question here is this. They want the speed of the ball, okay? So this one is a very important term you need to identify. They're not asking you about the horizontal velocity. They're not asking you about vertical velocity. They're asking you about the speed particularly. When you see the term speed, this one is actually kind of relating to the resultant velocity. This is relating to the resultant velocity, okay? The resultant velocity of both horizontal and vertical components of velocity. So if I try and indicate to you what is speed here, speed will be this one, okay, resultant velocity. Speed will be something like this. Okay, I use a different color here. Just give me a moment for me to select a suitable color. Okay, I'll use all pink color. My speed is something like this. Okay, this is not a really good way of drawing it. Your resultant velocity or speed is always tangent to the path of motion. Okay, so when they ask you the speed right now, they're talking to you about this, which is the resultant of your Vy as well as Vx here. Okay, that's what they want you to find out. So you need to first find out what is your vertical velocity in the first place. So in your case, let's just go through this. If you're talking about the vertical motion, what is it that you know? You know that your initial vertical velocity is 0. You want to find out your final vertical velocity. You know your acceleration is equals to g. You know your time is equals to 3 seconds. But you also do not know what is your vertical displacement. Okay. Yeah, one thing I should probably mention to you here is how do I know that time is 3 seconds? Is because they've already written it here. Okay, they told you that your object will hit the ground in a time of 3 seconds. It basically just means something like this. If I move from here to here along this green path here, it took you 3 seconds, okay? But there's something that I've always kind of mentioned to you guys before. If your object took a curved path like this to reach this point here on the ground, it's actually a combination of 2 different motions in 2 different directions. If you were to move from this starting point to this end point here, you actually move horizontally like this, as well as vertically like this, okay? So you're talking about the horizontal motion part. From the start to the end, it will be 3 seconds. And then you're talking about the vertical motion part from the start to the end, it will also be 3 seconds. So that time what I mentioned to you guys before was this. There's one thing that links the constant velocity horizontally and the constant acceleration vertically. That one being that time taken to move horizontally to a point, is equal to time taken to move vertically to the same point. In other words, Ty is Tx. Sorry, Tx is equals to Ty. Okay, so that is one thing that you should have learned last time. Okay, so in my case, I am talking about vertical motion. The time is still 3 seconds, regardless. All right. So now that you identify all these little variables here, you know that your kinematics equation, there are 4 of them, right? V is equals to U plus AT, S is equals to half U plus VT, S is equals to UT plus half AT square, and then finally V square is equals to U square plus 2AS. So how do you know which one to use? You always try to list out the variables first and then identify the variable that you do not want. Now, the final velocity V is what you want to find out, but the vertical displacement is not something that you want to find out. So S is the unwanted variable. So whatever equations that you have here for the kinematics equation, just disregard anything with S inside. That would mean second, third, and fourth equation is out. You will only be using the first equation, V equals to U plus AT. So this one is the equation you want to use, then you just use it. Now, downwards is considered to be your sign convention because you're moving downwards in the first place. That's your initial direction of motion. So it's V equals to U plus AT is equals to 0 plus 9.81 times 3, eventually giving you 29.43 meter per second. Okay, so right over here is 29.43 meter per second for Vy. And your Vx is actually 10 meter per second. So from there, you can actually now find out your resultant. If you were to draw your velocities Vx and Vy from head to tail, this is what you're gonna get. This is Vx. This one is Vy. Your resultant is actually this one. Okay, so this one is your Vx. This one is 10 meter per second. Sorry, let me use a different color. This one is 10 meter per second. This one is 29.43 meter per second. So my VR here is the hypotenuse of this right angle triangle. So it's square root of 10 square plus 29.43 square. Eventually giving you 31.1 meter per second. Okay, so answer for this is C. All right, so that one is for this. Now, then you move on to question 7. Now, for question 7, an object is moving along the ground in a straight line at constant speed. Which statement about the resultant force acting on the object is actually correct here? Okay, so the thing here is you have an object moving along the ground in straight line at constant speed. Okay, so let's just say, for example, I have something like this, and I have an object that moves with constant speed like this. Sorry, let me just change the color again. This one they told you is constant speed. Okay. Okay, what's the significance of constant speed? If you have constant speed, that means your acceleration is 0. Your F net is 0. Okay. So that is the main thing to note from here. You have constant V here. So when constant V is, you have constant velocity, the main thing is net force is 0, resultant force is 0. So in your case, if you look at answer choices A, they say the resultant force acting on the object is equals to the weight. This one is actually wrong. There's not supposed to be any resultant force at all because you're moving at constant speed. And also in the first place, this is actually wrong because you're talking about vertical forces. Here, if you look at your diagram here, you're supposed to have a weight W downwards and a normal reaction force R upwards. There's no resultant force at all. You're not supposed to have a resultant force equal to your weight. If anything, it should be the reaction force equals to your weight. And then you look at B, the resultant force acting on the object is equal to the product of its mass and velocity. The thing that is wrong here is this one, because F net is the product of mass times acceleration. This is the thing that is wrong. And then the resultant force acting on the object is equal to the resistive force. This one is also again wrong because I already mentioned resultant force should be 0. Okay, so the last answer should be the correct one. Resultant force acting on the object is equals to 0. So answer is D. Okay, so that's for that. Then if you're okay with this, let's move on to question 8. Okay, now for question 8, water flows out of pipe and hits a wall. When the jet of water hits the wall, it has horizontal velocity v and a cross-sectional area A. The density of water is rho. The water does not rebound from the wall. And what's the force exerted on the wall by the water? Okay, now what's the significance of water does not rebound from the wall here? What's the significance is this statement? It just simply means that velocity of water is 0 after hitting the wall. Okay, if your water does not rebound, it just means straight away that the velocity of water is 0. Okay. If it rebounds, that means it would have some sort of velocity. But if it does not rebound, it just means velocity of the water is 0 here. Okay, so I could have a velocity v here right now, but upon hitting the wall, my velocity here is 0. Okay, so the question is asking you, what is the force exerted on the wall by the water? Now, in your case, this one, you have to make use of the definition of force that you've learned before. Force is defined as rate of change of momentum. Now, change in momentum here can be mass times change in velocity. Okay, mass times change in velocity is the mass times the change in velocity divided by, sorry, this one I wrote it wrongly, this is delta t. Okay, now when you say change in momentum, it can be mass times change in velocity or change in mass times velocity. Both cases are slightly different. In the first case, this one is constant mass, but velocity is changing. In the second case, velocity is constant, but mass is changing. What you're having here is actually the first case. Mass is constant, but velocity is changing. So in my case, this one is m delta v divided by delta t. Maybe I just replace it with t only. Okay, so what's your change in velocity? If you look at this part here, before this is v, then after that is 0, right? Your change in velocity is actually just v itself. So from here, I substitute this one in. This one will give me mv divided by t. But I still cannot get anything related to my answer, right? You will have to make use of the definition for density. Density is defined as mass over volume, right? Okay, make sure you write the v in a different way. This one v is volume, not speed. Okay, so volume is actually area times length, because if you look at it this way, this one is your volume of water. You have length L here, and then you also have area A here. So area times the length will give you your volume. Okay, so what do you want to do with this is you want to get what is your mass. Mass is rho v, which in turn is rho AL. Okay, so in your case, you sub it in, you will now get this one. You will get rho AL B divided by T. Now from there, you get rho A L over T times V. L over T is actually equals to velocity. So you get rho A V times V. Therefore, rho A V squared. Your answer is D. Okay, so that is for question 8. Okay, so if this is okay, then we move on to the next one. So I'll clear this one. Okay, then if you move on to the next one, question 9, you have a projectile that is launched at an angle above horizontal ground and travels through the air. The projectile reaches its maximum height at position X. Assume that no upthrust acts on the projectile. Which diagram shows you the directions of force or forces acting on the projectile at X? Okay, now, I believe I would have mentioned this to you guys before when we were doing kinematics and then after that dynamics. I mentioned to you guys before, if your question doesn't mention anything about air resistance being negligible, you are always to assume air resistance is present. Okay, this one I think I've already iterated it a few times before. If air resistance is not stated to be negligible in your question, always assume it is significant. Okay, or in other words, always assume air resistance is present unless otherwise stated. Okay, there's another different way of wording this. Always assume air resistance is present unless otherwise stated. Okay, so in your case, your question never say anything about air resistance being negligible. You are to assume that it is significant here. Okay, so the part where here they say is traveling through the air, you have to assume air resistance is significant. Okay, right? So from there, what do we then know? Okay, there's a few facts here that again I need to rewrite. So just now this one is something I wrote before. Speed is always tangent to the path of motion. So I already explained to you, speed is actually the resultant velocity, or sometimes you guys learn it as instantaneous velocity. Same things too. Okay, but it's easier for me to write it as resultant velocity. Okay, it's instantaneous velocity too. Okay, so speed is always tangent to the path of motion. And then speed or direction of motion. Okay, what I wanted to say is this. Speed is always tangent to the direction, it's always tangent to the path of motion. Direction of motion is also always tangent to the path of motion. Is also the same. Okay, let me just write this. Direction of motion is also the same. Because right now you're talking about considering the forces acting at position X, right? If you're talking about position X, you're already at maximum height. The direction of your motion or the direction of your speed is actually tangent to that path. So it will actually be like this. This one is actually your direction of motion or speed. Okay, they are both interchangeable. So from there, what can you then do? You know that air resistance always opposes direction of motion. Now that you already determined that air resistance is significant, where is the direction of air resistance? Air resistance always opposes direction of motion. So in your case, if you already established that the motion is going towards the right at position X, your air resistance is obviously going to oppose it. So this is the direction of your air resistance going towards the left. Okay. And at the same time, there's also another force here acting on your object. That is actually your weight W. And you also have your weight. So weight is always vertically downwards. Okay, this one, no exceptions, always vertically downwards. So in your case, what is the forces acting on the projectile at position X is obviously going to be B. This one is your air resistance. This one is your weight. Okay. So that one is for this one. So pretty straightforward. But let's just say the question go and change a little and they ask you what's the direction of forces acting at this point. So in your case, if you're asked about the direction of forces acting at this point, your weight will still be downwards, but your air resistance will be tangent to the curve, but upwards. This one will be the direction of your air resistance. Okay, let's just say if the question changes a little and they go and tell you it's somewhere around here, you will still have the weight acting downwards, but your air resistance must be opposing your direction of motion. It will be diagonally outwards because the direction of your motion is diagonally downwards here. Okay, this is just some extra thing for you to know in case they go and change the question next time. Okay, then if you're okay with this, then we move on to part 10, question 10, which is a statement of the principle of conservation of momentum. This one everyone should know by now. Now, A, a force is equal to the rate of change of momentum of the object upon which is x. This one is out. This one is definition of force, not conservation of momentum. Then look at B. In a perfectly elastic collision, the relative momentum of the objects before impact is equal to the relative momentum after the impact. This one is again wrong. It's not really talking about conservation of momentum because you're talking about perfectly elastic collision. One thing that always comes out when it concerns perfectly elastic collision is this: your relative speed of approach must be equal to relative speed of separation. So what is wrong about this statement here is the fact that talk to you about relative momentum. It should be relative speed of approach equals to relative speed of separation. Okay, that is for B. All right, they use the wrong term here. And then for C, the momentum of an object is the product of mass and of the object and this velocity. This one is not conservation of momentum, but rather it's the definition of momentum. All right, so that leaves you with only answer choice D as the correct one, where they tell you the total momentum of a system of interacting objects remains constant provided no resultant external force acts on the system. Okay, so when they say no resultant external force acts on the system, this is already implying to you that it's a closed system. Okay, and one thing about conservation of momentum that you guys would probably have always remembered is this: sum of your initial momentum is equals to the sum of your final momentum. In other words, total momentum before collision is equals to total momentum after collisions, right? So they sometimes can be worded in a different manner. This particular equation here, which is an expression of principle of conservation of momentum, can be sometimes worded differently. Sometimes they call this as total momentum conserved. Sometimes they call this total momentum constant. Okay. Yeah. Okay, so for this total momentum is conserved. Because this total momentum is constant, or they will also sometimes call this no change in total momentum. Okay, so sometimes conservation of momentum is not, I mean, there are other ways of saying it other than you saying that total momentum before collision is equal to total momentum after collisions. There are a few other statements that are used to describe the same thing. Either you say momentum is conserved, momentum is constant, or no change in the total momentum. Okay. Yeah, also bear in mind, you must always use the word total momentum. Okay, it's a keyword. Okay, question 10 is all right. Then we go on to question 11. So I'll clear off the diagram here. Now, in question 11, you have a horizontal wooden plank that is pivoted at one end as shown here. The plank has a mass of 100 kg and a length of 10 meter. The center of gravity of the plank is a distance of 4 meters from the pivot. What is the moment of the weight of the plank about the pivot? So in your case, this is pretty straightforward. They just want the moment of the weight of the plank about the pivot. So in your case, they already gave you the mass, they already gave you the length, they already gave you where's the pivot. So your weight will act through the center of gravity, which is right over here. Your weight is W equals to mg here. Okay. So because we already told you this is the center of gravity, we know weight acts through this point. Okay, the center of gravity. So you want to find out the moment now. Moment is force times perpendicular distance. It is weight times perpendicular distance now. It's going to be basically 100 times 9.81 times your perpendicular distance of 4. Your perpendicular distance is the distance between your force and your pivot. So this one is your perpendicular distance. All right. So 100 times 9.81 times 4 gives you 3,924 Newton meter, which is actually 3.9 times 10 power 3 Newton meter. The nearest answer is actually C, if they round it out to 1 SF. Okay, so that's that. And then you have the last part here, question 12. When must an object be in equilibrium? All right. Now, in your case, notice that they kind of bolded this particular word, must be in equilibrium. So when must an object be in equilibrium? You already know that equilibrium must satisfy two conditions in the first place. For something to be in equilibrium, you must have no resultant force in any direction, which basically means this now, sum of fx is 0, which also means rightward force equals to leftward force, and then sum of vertical forces is 0, which in turn means upward force equals to downward force. And then the next one being no resultant moment about any point, which in your case would mean this sum of moment is equals to 0, which can be translated to clockwise moment equals to anti-clockwise moment. Okay, this is the full condition for equilibrium. So you look at the answer choices. When no resultant force acts on the object, this is actually just the first condition. For something to be in equilibrium, you must satisfy both conditions, the first and second. No resultant force, no resultant moment. So A is out because it's only stating the first condition. So if you look at B, when no resultant force and no resultant torque acts on the object, this one should be the correct one, because they say no resultant force, no resultant torque. Torque can be changed to moment, they're interchangeable. Okay, so B is the correct answer here. So if you look at the next few answer choices, no resultant torque acts on the object, this is just the second condition only, not the full condition. All right. And for answer choice D, when the upward force on the object is equal and opposite to the weight, this one is actually not necessarily true. I mean, the question said what the condition where the object must be in equilibrium. So what if I have an object that's going, a ball that's floating up, a ball floating up in water at constant speed? Let's just consider a case where I have a ball that's floating up in water at constant speed. So this is the ball. You have upthrust, you have weight, you have drag force. In my case, because it's in equilibrium, upward force must be equals to downward force. So weight plus drag force equals to upward force. So my upward force is this one. Sorry. I cannot rewrite it differently. Just give me a moment to rewrite this. This one, upward force is equals to W plus D. Okay. So here you see my drag force is my outward force, but is actually, it must be equals to my downward force. But my downward force is actually not just the weight alone, it's including the drag force. So you're saying that for something to be in equilibrium, the upward force must be equal and opposite to the weight. This is actually wrong. You could have certain cases where the upward force is equals to weight plus drag force, some other force, not just the weight. Okay, so that's for question number 12. All right, so this question is actually on equilibrium again, but they kind of modify it a little to be something complicated. Now, in question 13, you have a uniform diving board that is held by two fixed rods at points P and Q. A person stands at NR of the diving board as shown below. The forces exerted by the rods on the board are vertical. The board remains in equilibrium as the person slowly moves towards point Q from NR. Which row describes the changes in the magnitudes of the forces exerted by the rods on the board? Okay, so let me just try and zoom in a little. Okay, so that it's easier for us to see this question. Okay, so in my case, you want to find out how the magnitude of the forces exerted by the rods change. Let's just first identify what are the forces acting on your board. Okay, you have the person standing at R who's having a weight of W here. And then after that, you have the rods at the other end. So you see, the thing now is this. When your plank is like this, initially, once you have a person standing at the other end, it has a tendency to tilt like this. Okay, so you can imagine that this end of your plank is actually pushing up on the rod P. So if it's pushing up on rod P, this one maybe I should probably write push up on rod P for this one. And then this other, for the end here, the furthest end here, the plank will push out on rod P. So if it's pushing out on rod P, the force exerted by rod P on the plank must be downwards. In my case, it's like this. This one, let's call this force FP. All right. And then after that, if you look at the other rod Q here, as the plank is actually tilted like this end here would actually be resting on the rod. So this one is actually pushing down on rod Q. So since it's pushing down on rod Q, the force that rod Q exerts on the plank must be upwards. Let's call this FQ now. Okay, so let's call this force FQ. They already mentioned that all the forces are vertical here. All right, so there are no diagonal forces, no horizontal forces whatsoever. All right, now from here, they also mentioned that your board is supposed to remain in equilibrium. Okay, this is the most important thing. Your board remains at equilibrium when the person slowly walks towards point Q from NR. So your person is actually moving towards this direction. This is the direction of motion of your person. So as it moves towards the left, you're still maintaining equilibrium throughout. Okay, so if you're talking about equilibrium, which condition of equilibrium that you want to use? You would want to use the second one, where we mentioned that there's no resultant moment about any point. In other words, clockwise moment equals to anti-clockwise moment about any point. All right. Now, before you can go and do anything with this, let's just consider this too. Now, when you're talking about moment of a force, you will often say moment is force times perpendicular distance, right? Okay. So that is one part here. You have three things to consider here. If for the person, I apply m equals to F times delta D, as the person is moving from the right towards the left, F is constant. Okay, let me just write it out for you. If I'm talking about the moment of the person itself, it will be his weight times perpendicular distance of the person. Now the weight is constant. Therefore, the moment of the person is proportional to the perpendicular distance of the person. If you're talking about rod P, the moment of rod P is equals to the force of P times the perpendicular distance of P. Okay. Now, in my case, when the person is moving towards the left, force Fp can change. That's what the question is asking here. But the perpendicular distance between the force Fp and the pivot itself will never change. It remains fixed. So this one, if I'm talking about perpendicular distance for rod P and the pivot, perpendicular distance between the force at rod P and the pivot, this one will be constant. Okay. So because this one is constant, I can now say something like this. Perpendicular distance for P is constant. Therefore, moment of P is perpendicular, is directly proportional to the force of P. Now you apply same reasoning to rod Q. Moment of Q is force of Q times with the perpendicular distance of Q, which in your case, this one remains constant too, because it cannot change. So if that's the case, perpendicular distance of Q is constant. Therefore, moment of Q is perpendicular. So moment of Q is directly proportional to force of Q. Okay, so these are some things to note first. Okay, now is where we start to apply equilibrium condition. So if you're applying equilibrium, where you say clockwise moment equals to anti-clockwise moment, there are two different points that you can choose as your pivot right now. All right. So in my case, if I take moments about P, if I take moments about P, let's just say P is now my pivot. Let's just try and write this out. My P is now my pivot. You see, FQ will cause a counterclockwise rotation, but the person will cause a clockwise rotation. So in my case, I can actually say that moment of the person is equals to moment of Q. All right. So now the thing is this: if my perpendicular distance of the person to the pivot has decreased, that means the moment of the person has dropped. And so would the moment caused by Q. And then if you take note of what was written here, if moment Q decreases, so would force FQ. Okay. So here, if moment Q decreases, so would force FQ. Okay, this is for this part. Then if you then say, take moments about Q instead. So now your new pivot is right over here. Let me just erase this one. Your new pivot is right over here about Q. This is now your new pivot. So what does the moment caused by FP look like? It will be counterclockwise, whereas the moment caused by the weight will be clockwise. You see, they are equal and opposite. They should be equal and opposite if they're in equilibrium. So I could actually say the same thing here. M of person is equals to M of Q. But since perpendicular distance of person is actually dropping, that means the moment caused by the person is dropping. The moment caused by P, sorry, I wrote this wrongly. This one, moment caused by person is equal to moment caused by P. Okay, so if moment caused by person drops, the moment caused by P will also drop. And then likewise, you will get the same reasoning again as before, where you say that in my case, since moment P is dropping, force of P is dropping, because you can see the relation right over here. Okay, so in your case, force FP drops, force FQ drops. It should be answer choice A. Okay, that's for this particular question. All right, so if that one is okay, then maybe I move on to question 14. Now, for 14, you have a solid block that has sides of lengths L, 2L, and 4L. The block is submerged in a water of uniform density so that the faces with the largest area are horizontal as shown in the figure here. The upthrust acting on the block is U. Then the block is now rotated to a new position so that the faces with the smallest area are horizontal. The block remains fully submerged in water. What is now the upthrust acting on the block in this new position? Okay, so one thing to note here is this. They mentioned that the block remains fully submerged inside your water. Okay, so what you have here is the before they go and change the position. All right, now after they change the position, it could probably look like this. After they change the position of the block, it could probably look like this now, with the smallest area horizontal. Okay, but it still nonetheless remains fully submerged below the water. Okay, so in your case, what you learned before for upthrust was this. We mentioned to you upthrust is actually the weight of liquid displaced, which in your case is rho Vg. Okay, so this V here relates to the volume of liquid displaced, whereas this rho here relates to density of your liquid. Okay, so in your case, if you look at your question, before it was this example, then after that you go and tilt your block so that this is now your case, this is the after case. Now, what can you say about the volume of liquid displaced? In your case, if you see, if you go and tilt it with the smaller space horizontal, but still fully submerged inside the water, you will probably say that volume of liquid displaced remains unchanged. Therefore, weight of liquid displaced and hence upthrust remains the same. Again, that's what you can say here. You notice that the volume of the liquid displaced has not actually changed. So from there, you can infer that the weight of liquid displaced must not have changed, and therefore upthrust must also remain the same here. So in your case, if before this your upthrust was U, it must also be U now. Okay, if upthrust is U, before your upthrust must still remain at U now. Okay, so answer for this is B. So that one is all right. I'll just clear this one off and move on to the next one. Okay, next one is on density. Okay, for question 15, in a large container inside oil refinery, 3 oils of different densities are mixed. No chemical activity occurs. The mixture consists of three different oil, 1,200 kg of oil of density 1,100 kg per meter cube, 1,500 kg of oil of density 860 kg per meter cube, 4,000 kg of oil of density 910 kg per meter cube. What is the density of the mixture? Okay. Now, the wrong way to do this would be to do something like this, where you say the density of the mixture is density 1 plus density 2 plus density 3 divided by 3, where you basically say is 1100 plus 860 plus 910 divided by 3, giving you some sort of answer where you get 956 kg per meter cube. So this one is actually the wrong way to go about in doing this. All right, this is not the correct way. When it comes to density of any particular mixture, you always go to the basics where you say it is mass total divided by your volume total. Okay, you have to find the total mass separately, you have to find the total volume separately before you can actually find out the density of the mixture itself. So in your case, you remember that density is mass over volume, right? If I'm interested to find out the volume here, since I already know the masses, the volume would actually be mass divided by density. Okay, so here let's just put in the values. Your mass total will be 1200 plus with 1500 plus with 4000 divide with 1200 over 1100 plus with 1500 divided by 860 plus with 4000 divided by 910. So from here, your density value ought to be 927 kg per meter cube. This one is if you calculate it out. So your answer should have been A. Okay, it will not be C. All right, so that is for this particular question. Then you move on to question 16. Now for question 16, they mentioned this for you. You have a box that slides down a rough ramp. The change in gravitational potential energy of the box is 16 joules as it moves between positions X and Y. The box has 24 joules of kinetic energy at X and 35 joules of kinetic energy at Y. So in your case, you have KE of 24 joules here, and you have KE of 35 joules here. Okay, so how much work is actually done against frictional force? Now, in the first place, when they tell you that you have a rough ramp here, this one already means friction is present. Okay, so they want you to find out what is the work done against the frictional force. So in my case, you need to apply conservation of energy. Now, first things first, we know that GPE decrease because height has decreased, and we know KE has increased because it went from, because KE changed from 24 joules to 35 joules. Okay. Now, if you apply conservation of energy, I mentioned to you that you could probably try and summarize conservation of energy as one particular equation where I mentioned to you whatever energy that you lost is going to be the energy you gain plus work done against any friction. So in my case, is GPE loss equals to KE gain plus work done against friction. So my GPE loss, I already know the value as 16 joules. My KE gain will be 35 minus 24 plus work done against friction. So therefore, work done against friction would therefore be 35 minus 24 is 11, 16 minus 11 is 5 joules. So my work done against friction is 5 joules here. So answer is A for this one. All right. Okay, now if you move on to the next question, question 17. Question 17 mentions this. Wait, I'll change the color. The total useful energy supplied to an electric motor is E. Energy Q is wasted, and the remaining energy does useful work. What is the efficiency of your motor right now? Okay. So here again, you kind of apply conservation of energy, but you'll be something like this, where you say total energy is equals to useful energy plus wasted energy. So you sub in the relevant variables that's defined by your question. Total energy is E. Useful energy remains as useful energy. That's what you want to find. Then wasted energy is Q, right? So useful energy is going to be E minus Q. This is number one. But the question wants you to find the efficiency of your motor right now. So in your case, efficiency is generally useful energy divided by total energy. So it's actually going to be E minus Q divided by E. But you notice there's not the answer given here, right? So you have to kind of do something with this. You go and take E divided by E, you take Q divided by E, you will eventually get 1 minus Q divided by E. So in your case, your answer would be C. Okay, that is for this particular question. So 17 is done. We move on to question 18 then. Okay, question 18. Let's clear this one off. Okay, now for question 18, you have objects with different masses that are placed on the horizontal surface of a table. The objects are then raised to different heights above the table. The gain in GPE of each object is the same. Which graph best shows you the variation with height h of the objects above the table and the masses m? So a very important statement here in your question is this: the gain in GPE of each of the object is the same. So it will probably be better to visualize what's happening. Let's just say that this is your table and you have three different masses. Let's just say that I have mass M1. Let me just redraw this properly for you. Say right now I have mass M1. I raise it to a height of say H1 over here. And then after that, I have mass M2. It's a different mass. This is mass M2. I raise it to another different height, maybe say right over here. This one is raised over a height of H2. And then lastly, I have mass of M3. I raise it all the way high up to here maybe. Okay, so this one is height H3. So I have different masses, different heights. But what the question did mention to you here is that the change in GPE for all three is supposed to be the same, because you see, they mentioned the gain in GPE of each of the objects is the same. So what this essentially means is this: change in GPE of 1 is the same as change in GPE of 2 is the same as change in GPE of 3. The change in GPE is the same for all three different masses. Okay, so in my case, if I look at the equation for GPE, is mg delta h. Now, this part alone at the top already tells me change in GPE is constant. I apply change in GPE equals to mg delta h for all the three masses. Okay, I apply for M1, M2, M3. So I can say this: change in GPE and G being constant, I will get mass is inversely proportional to height. Okay, maybe I should just write this as h now, because h here is already changed in height following your question. Okay, so mass is actually inversely proportional to height. Or put it another way, height is inversely proportional to mass. Let's just follow what the question wants. Height is actually inversely proportional to mass. Okay, so if you were to draw a graph of mass versus, you were to draw a graph of height versus mass, like what the question wanted, you are supposed to get a curve like this. The answer is actually A. Okay, now why do I say it's like this? The graph shape is like this. You probably would have learned this in maths before. If I tell you that you have y is inversely proportional to x, and then I subsequently ask you to draw a graph of, say, y versus x, like this, you would have said that it should be a curve that looks like this, right? With the asymptotes as the x and y axis. So it's actually the same case now, just that the variables are different. Okay, so that one is for this particular question. Then we move on to question 19. Okay, question 19. You have two wires P and Q that are made from the same metal and hang vertically from a steel girder. Wire Q has half the length and twice the diameter of wire P. Identical masses are now attached to the bottom of each wire. Both wires obey Hooke's law as they are stretched by the weight of the masses. What is the ratio of extension of wire P to that of wire Q? Okay, so for this one, you can probably imagine it as something like this. Let me draw it right over here. Okay, you have two different wires. Say this is the first wire. It is short and fat, I think. It's a bit short and thick. And then the second one is something like this. It is long and thin. Okay, these are the two wires. One is wire P, and then the other is wire Q. All right. So what you're interested in is the extension. Okay. So bearing in mind that right now you also have some sort of weight that is being applied to them. Wait, now let me just draw this out. You have weight W. So this one was wire P, and this one was wire Q. All right. Okay, so if you want to find extension for any kind of wire, there's always one equation you always use. That one being this particular equation. E is the ratio of stress to strain. Is force over area divided by extension over length, giving you FL over AE. So extension E is what you want to find. So E is FL over area times Young's modulus. Okay. So this equation applies to both of the wires that you have hanging over the steel girder right now. But before you can do any kind of ratio, you need to always identify what is the same for both cases. So the first part where they say same metal already means same E. And then after that, they say identical masses are attached to both wires. This one already tells you same force. All right. Everything else is different. So in your case, you could probably say this F and E constant. If F and E is constant, that means E is actually inversely proportional to, directly proportional to F over A. Sorry, I forgot something here. This one should be FL over pi over 4D squared. I forgot to expand the area. Okay. So if I say force and Young's modulus is constant, that would mean extension is directly proportional to L over D squared. Okay. So that's what you have here. Now, there's an easy way to go about this, and there's a more tedious one. I just show you the easy one first. If you're talking about the easy way of doing this, now you just look at for wire Q itself. Okay, for wire Q, you make a comparison for wire Q. For wire Q, the length is actually half the length of P. So that means the length is actually reduced by 2 times. That would mean the extension is reduced by 2 times too. And then after that, when you look at the diameter, they told you that the diameter is twice that of wire P. So the diameter is 2 times more. The extension should actually be less by 4 times. Because you see this one is an inverse relation and there's a square here. So if one of them is increased, one of them must be a decrease. And because there's a square, the value is squared. So over here, what you can then say is this. Therefore, overall E decreased by 9 times. Sorry, decreased by 8 times. Overall E decreased by 8 times for wire P. Okay. So from here, you can say that EQ is actually 1/8 of EP. So EP over EQ is going to be 8:1. The answer is supposed to be A here. Okay. This is how you can do this in one way. Now, you want to do it the tedious way is something like this. The tedious way is something where you write it like this. Maybe I use black color here. You can say that because E is proportional to L over D square, you can subsequently say that EP, sorry, use a different color, black color, please. Okay, EP to EQ is actually LP to LQ times with DQ square over DP square. So when you try to really sub in the values, you are going to get something like this: LP over half LP, because LQ is half LP here. And then DQ is actually twice of DP. So this one is 2 DP. Don't forget to square, divide by DP square. Eventually, you will get the answer as 8:1. It's just 8 lah, but it's the same as 8:1. So answer will still be A. Okay, this is the more tedious method. All right, up to you to decide which one you want. Okay, if this is okay, then we look at question 20. We're only halfway through the paper. Yeah, question. Okay, which statement about elastic and plastic deformation must be correct? Okay. So which statement must be correct in the first place? So if you're talking about elastic deformation returns to original length after force is removed. And this is elastic deformation. But when it comes to plastic deformation does not return to original length after force is removed. In other words, there is permanent extension. There is permanent extension or deformation. All right. So looking at the answer choices, the obvious answer is actually D. Elastic deformation is reversible, but plastic deformation is not. Okay. When it's reversible, it means you can go back to the original length. When it's not reversible, that means it doesn't go back to the original length. There's some sort of permanent extension. Okay. For the answer choices A, B, C here, elastic deformation and plastic deformation are proportional to applied force. Elastic deformation and plastic deformation cause no change in volume. Then elastic deformation causes heating of material, but plastic deformation does not. This one is not necessarily true always. Okay, the question wants the condition that must always be true all the time, 100% of the time. So A, B, C is definitely out. It occurs for some cases, it doesn't occur for some cases. All right, but D definitely is 100%. Okay, it's always that case. All right, so if that is okay, then we move on to question 21. This one is really waves. All right, now for waves, this one is pretty straightforward. Now the graph here shows the variation with time of the displacement of a particle as a progressive wave passes through. And what are the frequencies and amplitude of the wave here? So they want this particular case, the frequency and the amplitude. So in my case, this is a displacement time graph. So since this is a displacement time graph, I can easily identify what is my period here. My period is actually going to be this one. Okay, my period is 10 nanosecond. So frequency is the reciprocal of period, is 1 over 10. Because it's in nanoseconds, I must remember to change it from nanosecond to second. So I get 1 over 10 divided by 10 power divided by 9. I get 100 times 10 power 6 hertz. In other words, 100 megahertz. And then you're talking about amplitude. Amplitude is going to be this one. Okay, by you just looking at the graph itself, this one is 5 millimeter. Okay, so what is your answer here? Your frequency being 100 hertz and your amplitude being 5 millimeter, your answer should be A. Okay, for 21. All right, so this one is pretty straightforward. Then I'll move on to the next one. Okay, so what about question 22? Okay, now for question 22, this is what you have. Now the graph shows the variation of displacement of an air particle with time as sound wave passes through the air. This is still a displacement time graph. From there, they mentioned that the intensity of the sound is half while the frequency remains constant. The 4 graphs below are drawn to the same scale as the graph above. Which graph shows you the displacement of the air particle now? Okay, so one important thing to note is that the graphs that you have below are drawn to the exact same scale as the one above. And they told you 2 important information. Intensity of sound is half. And also frequency remains constant. So each of these is supposed to mean something for you. Okay, so first thing, intensity. Intensity is directly proportional to amplitude squared. This is what you've learned last time. Okay, so in your case, intensity of sound is half. You can think of it this way. Second, I2 to I1 is amplitude 2 square to amplitude 1 square. So my intensity is half. That would mean I2 is half of I1. Okay, so I want to find the new amplitude. Now my old amplitude, the A1 here, I can just give it an arbitrary value of 4 boxes because you can see there are 4 boxes here. So this one, let's just give it a value of 4 boxes. So A2 squared would actually be, sorry, I forgot to square this one, all right, because it's A1 squared. So this one will actually give me 8. 16 divided by 2 will give me 8. So A2 is actually the square root of 8, giving you 2.8 boxes, which is roughly 3 boxes. Okay, so later on you need to have a graph with 3 boxes only. This is the first one. And what is the relevance of saying frequency is constant? Frequency is actually inversely proportional. Frequency is actually the reciprocal of period. So in your case, you know that frequency is constant. Period must be constant too. So in your case, if T1 is, say, 4 boxes, T2 must also be 4 boxes. So look at your graph. Find the one with period of 4 boxes and amplitude of 3 boxes. You should get the answer as D, because you can see this one is 4 boxes, and then this one is 3 boxes. Okay, so that one is for this. Now, There's another method in which you can do this one also. This one is the so-called quick method. Now, in my case, if I know that my intensity is decreasing by half, my amplitude here is actually decreasing by square root 2. Okay, so now if I try to find out my new amplitude, it's actually going to be 4 boxes divided by square root 2. 4 boxes divided by square root 2, you should get that 2.8 also, which is going to be the same as 3 boxes. No? Okay, it's going to be the same. All right. But in your current case, this one may not be the easiest one. All right. That's why I started off with the other method just now. Okay, so if this is okay, then let me just move on to question 23. Now, question 23, which statement is correct? Let's go through this one by one. Now, gases cannot transmit longitudinal waves. Is this statement correct or false? This statement is false. Why? Because sound waves can travel through air. Sound wave is longitudinal wave. Air is gas, isn't it? Sound waves can travel through air, so A is wrong. And then after that, if you look at the second one, longitudinal sound waves cannot form stationary waves. This one again is wrong. Why? Because the loud sound heard over air column, sorry, not heard over air column, the loud sound heard from air column inside a cylinder, from air column inside cylinder is stationary sound waves. You know the questions you always do where they say you always hear the loud sound over the air column inside the cylinder, that is actually stationary sound waves. So they say cannot form stationary sound waves. This is actually wrong. Okay. And then if you look at D, D is a wrong one also. They told you transverse waves cannot pass through a vacuum. This is again wrong. EM waves can pass through vacuum, isn't it? EM waves is actually transverse wave. So D is definitely out. Okay, so that would mean that your only possible answer is actually C. C is supposed to be the correct one. Now, solids can transmit both transverse and longitudinal wave. This is correct. So how are you going to visualize this? Why do we say solids can transmit both transverse and longitudinal wave? You imagine this. If I told you you have a glass, transparent glass, you shine light onto the glass. If you have someone right over here, you can actually see the light, right? So that would mean that transverse wave can pass through solids. Glass is solid, okay? Light is transverse wave. So you shine light through glass, you can actually see the light at the other end, right? So this is actually proof that transverse wave can pass through solid. And then likewise, if you're talking about sound waves, say for example, I have sound waves that I transmit to the glass. If you were to just put your ear close to the glass, you can also hear the sound wave, right? So this is also proof that longitudinal wave can pass through solid. So answer is definitely C. Okay, so that's for this particular question. All right, then after that, we move on to another one. Okay, 24 is Doppler effect. Okay, maybe I will have to finish off this Doppler effect one. Then after the rest, maybe I don't have time. I may have to do it separately in a different session. Okay, let's just do this Doppler effect thing. Okay, this one is actually quite long-winded. Okay, a car is traveling at constant velocity towards a man that is standing in the middle of the road. The driver sounds the car's horn as a warning. The horn emits a sound wave of constant frequency. The frequency of sound heard by the man is different from the frequency of sound the frequency of sound emitted by the horn. Which statement here is correct? Okay, so this one being Doppler effect, you often would try to single out two things. If it is approaching observer, what you will always say is observed frequency is going to be more than your source frequency. But if it's the opposite case where it is moving away from observer, you would then say that observed frequency is less than your source frequency. Okay, and that's in general what we normally say or do lah. Okay, now here, if you look at the answer choices one by one, the frequency of the sound emitted by the horn is greater than the frequency of the sound heard by the man. This one is actually implying to you that the observed frequency is less than source frequency. Okay, so the case that we have here is the case where a car is traveling at constant velocity towards a man. This is actually approaching the observer. So this one I already know is approaching the observer here. So therefore, F observed frequency must be more than source frequency. So A is definitely out. It cannot be less. It must be more. Okay. Then if you move on to B, the frequency of the sound heard by the man depends on the distance between the car and the man. This one is actually wrong. Actually, it actually depends on speed, not distance. Okay, this one I will explain in a little while. So B is wrong. And then after that, if you look at the next possible answer, this one, C, the sound waves continuously accelerate as they move from the horn to the man. This one is also wrong. The speed of sound is constant. Speed of sound constant. The reason why I say it's constant is because your sound is moving through same medium. Okay, if your wave is moving through the same medium, the speed will never change. It will always remain the same. Okay. All right. So C is wrong. Okay, now last answer ought to be the correct one, where they tell you the wavelength of the sound heard by the man is less than the wavelength of sound heard. Is less than the wavelength of sound emitted by the horn. Okay, the term they use here is not frequency, they use wavelength. Okay, so they kind of change the answer a little here. So what do you know about wavelength now? Okay, so we know that if you're approaching observer, your observed frequency must be more than source frequency. Okay, that's what we know. Now, let's try to relate it to wavelength. If you know V is equals to F lambda, I already mentioned to you speed is constant here because you're moving through the same medium. F is inversely proportional to wavelength. Okay, so that would tell you that if frequency is large, wavelength is small, and vice versa. Okay, so how does this relate to approaching the observer case? If you apply this one to this equation over here, because my observed frequency is larger, you see, so F naught is larger than Fs, therefore wavelength observed is less than wavelength of the source. Okay, so if I already know that the relation between wavelength and frequency is that they're inversely proportional to each other, now that I have a case approaching the observer where observed frequency must be more than source frequency, I will have something like the inverse relation here. Observed wavelength must be less than the source wavelength. So this is actually what is being described here. This is observed wavelength less than your source wavelength. So this is the correct answer. Okay, so that's for that. Okay, now from there, there's something I kind of need to explain a bit further for you guys. Just now I told you about B, right? The frequency of sound heard by the man depends on the distance between the car and the man. It does not depend on distance. Instead, it actually depends on the speed. Okay, so let me just try to explain this. It might probably go another 5 or 10 more minutes. So let me just continue back on what I was talking about. Frequency change in Doppler effect depends on speed of the source. In general, the higher the speed, the larger the frequency change. Okay, now what do I actually mean by that? So let me just erase all certain things here because it's in the way. Let's consider this one, all right? So I have a case where you have someone that's approaching observer. Let's just say that my observer is here. And I have a few cases that I want to talk about. This one, this person moves to this source move like this. Okay, there are a few cases here. If I say that this one, the source was speeding up, then this part is constant speed, and then this one is slowing down as you're moving towards the observer. If I try to plot a graph out of frequency observed versus distance, let's just say that this one is, in my case, my observed frequency F0. This one is my source frequency. Then this one is just basically my distance. So like this. So my graph that I expect to see could probably look something like this. Like this, like this, and like this. Okay. Wait, I try to draw it out nicely. Okay. So notice that when it comes to the observed frequency here, my observed frequency is always higher than my source frequency right over here. But the amount by which they increase is different. For the case where I'm speeding up, you see the frequency increase is getting larger and larger and larger. But for the case where I'm at constant speed, the frequency increase is just constant. And then for the case where I'm slowing down, the frequency increase is actually getting smaller. Okay, but regardless of which case it is, because I'm still approaching the observer, my frequency observed will still be larger than my source frequency itself. Okay, so that's for this particular case. Now, what about the case where I move away from the observer? So this one, I probably have to draw it the other side here. Just give me maybe less than 5 minutes just to draw it out for you guys. Then we can just call it a day. So let's just say right now the source suddenly passed the observer. So my observer is right over here now, but my source keeps moving away like this, like this, like this, and then finally like this. So same thing again. We consider a case where you have a case where this one is speeding up, this one is constant speed, and then this one is slowing down. Okay, so now if I want to draw a graph of the frequency observed versus the distance, you now look like this. So same thing. I again have my observed frequency here. The axis, y-axis is my observed frequency, and then this one here is just my observed. This one, the x-axis itself is just my source frequency. Okay, and then this one is distance. So because I am moving away from observer, sorry, this one I better just write it now. This one, moving away from observer is different from the one at the top. Okay, so moving away from the observer, my frequency observed could be something like this, like this. Okay, I need to kind of draw the lines also just to clear, like this, like this. Okay, so my frequency observed would be something like this. Okay, so notice how the graph looks like now. Okay, so my observed frequency is always less than my source frequency. Okay, but again, because of the speed at which I'm moving, whether I'm speeding up, slowing down, moving at constant speed, my frequency decrease is going to be different each time. For the case where I'm speeding up as I move away, my frequency decrease is increasing. But for the case where I move with constant speed, the frequency decrease is constant. And then for the case where I'm slowing down, moving away from the observer, my frequency decrease is actually getting less and less. Okay, so this is why I mentioned to you for part B in your answer choice here just now, your frequency depends on your speed, not the distance. Okay, so let me just write something else here. Approaching observer, observed frequency must always be more than source frequency. Moving away from observer, your observed frequency must always be less than your source frequency. Okay, so this is the explanation for this Doppler effect. Okay, before I move on to question 25, let's just clear off everything on the screen here. In question 25, which statement about electromagnetic waves is correct? For answer choice A, a wave of wavelength 5 times 10 power minus 6 meter is invisible to the human eye. So it is invisible, that means it's not visible to the human eye at all. So in your EM wave spectrum, the only wave that is visible to your eye is actually visible light. So we know that the wavelength of visible light is actually between 400 to 700 nanometer. Changing it to meter, we will get 4 to 7 times 10 power minus 7 meter. So right now, just look at the power of tens of the wave. This is 10 power minus 6, but this is 10 power minus 7. So 10 power minus 6 is more than 10 power minus 7. So this wave is not visible light. Therefore, it is invisible. Okay, so answer choice A would have been correct here. But let's double confirm with the rest of the answer choices. So in B, they mentioned that the EM waves can travel at different speeds in free space. So different speeds in free space here is actually referring to vacuum. Okay, they are saying that the EM waves travel with different speeds in vacuum. So we know this one is definitely wrong, because all EM waves should travel with same speed in vacuum. So let me just write out the answer here. All EM waves travel with same speed in vacuum. Okay, no exceptions. And then if you look at answer choice C, they cannot be polarized. Now think about it. Electromagnetic waves are actually transverse waves. So since they are transverse wave, it can be polarized. Okay, so transverse waves can be polarized. All right, so answer choice C is definitely out, because only longitudinal waves cannot be polarized. Okay, then you look at the last answer choice D. They say that EM waves consist of vibrating atoms. This one is obviously going to be wrong. Now, in actual fact, EM waves are actually consisting of vibrating electric and magnetic field at right angles to each other. Okay, so an EM wave is actually made out of vibrating electric and magnetic fields at right angles to each other, not vibrating atoms. So all answer choices are wrong except A. A is correct. Now, then if you move on to question 26, a stationary wave is set up on a string that is stretched between two fixed points that are 48 centimeters apart. At one instant, the appearance of the string is as shown here. What is the wavelength of this stationary wave? Okay, so we are dealing with a stationary wave right over here, and they ask us to find out the wavelength of the stationary wave. So let's just imagine that our equilibrium position for the wave is right over here. This one represents the equilibrium position of our waves. So from here, we can identify the position of our nodes. These red points here would actually be our nodes. Okay, so let me just redraw it properly. So these points here, the red points are actually your nodes. Okay, so what do we know about distance between adjacent nodes in stationary waves? If you recall what you learned for stationary waves, it was already mentioned to you many times before that distance between adjacent nodes is equal to half wavelength. All right. So in our case, we know that the total length of this string is 48 centimeter. It's already stated inside the question. So let me just try to draw it out. We know that this one is going to be 48 centimeter. All right. This entire length is 48 centimeter. But how many half wavelengths do we have inside? We have one half wavelength here, another half wavelength here, and then another half wavelength here. So in our case, we actually have three half wavelengths. So three half wavelengths is equals to 48 centimeters. So if we solve this one, we get 48 times 2 divided by 3, we will get 32 centimeters. Okay. So that's for this one. Then we move on to the next question. So let me clear off the screen. Now, for the next question, a pipe closed at one end has loudspeaker at the open end. For some frequencies of sound from the loudspeaker, a stationary sound wave is formed in the air within the pipe with an antinode at the open end of the pipe. The length of the pipe is 0.85 meter. The speed of sound in air is 340 meters per second. Which frequency of sound for the loudspeaker would not produce for you a stationary wave? So notice that they emphasize for you which frequency cannot give you a stationary wave here. All right. So when it comes to stationary waves, remember what will always be the end conditions. I always mention to you that a closed end will be a node, whereas an open end would be an antinode, which is actually what the question has already confirmed for you here. They told you there's an antinode at the open end, and then after that, there is a node at the closed end somewhere. Where is it? Okay, they did not mention that. They just mentioned that antinode is at the open end, but by right, you should know that if it's a closed end, it must be a node. All right. So from here, what is the case that you're talking about when it comes to the formation of the stationary waves? You have fixed length, but changing frequency. Okay. The case that you're dealing with here right now for this stationary wave formation is a case where you have fixed length, but changing frequency. So let's just try and draw out the shape of the stationary wave that is possible. based on the situation that we have. So if you just give me a moment, let me just draw out the lines for you. You have something like this. This is the first wave. This one is the second wave. And this one is probably the third wave. Okay. So if you're talking about the first stationary wave, your first stationary wave formation would probably be something that looks like this. Okay. The second formation of your stationary wave will probably be something that looks like this. And then the third formation of your stationary wave would probably be something that looks like this. Okay. So in our case, remember I told you the length is fixed throughout. Okay, the length is not changed, only the frequency or the wavelength is changed. So let's just try to work out some sort of relation from here. Now in my case, I know this one is distance between an antinode and a node. So this one will actually be lambda over 4. Okay, so if I try to write it out, this one is lambda over 4. Sorry, lambda over 4 equals to L. All right. And this one will be occurring at frequency F0. So lambda is equals to 4L is occurring at frequency F0. And then if I move on to the second one, I could say that this one actually has 3 lambda over 4. You can see that this is a lambda over 4 here, lambda over 4 here, and a lambda over 4 here. So this one will actually be 3 lambda over 4 equals to L. So I will get lambda is 4L divided by 3. Okay. Notice what's happening here to the wavelength. So if you look at how the wavelength changes, you will notice that the wavelength has actually decreased by 3 times. So the frequency must therefore increase by 3 times. So how do I know this relation? It is from this, where I can say that B is equals to F lambda. If B is constant, F must therefore be inversely proportional to your wavelength. Okay, so if my wavelength has decreased by 3 times, my frequency ought to increase by 3 times. So instead of F0 now, I actually have 3 F0. Okay, then if I move on to the next one, the third formation of my stationary wave, you will notice that you actually have 5 quarter wavelengths as indicated here. Okay, so this one is quarter wavelength, this one is quarter wavelength, quarter wavelength, quarter wavelength, and another quarter wavelength. So in your case, what you actually have here would be 5 quarter wavelengths equals to L. And then wavelength here would just be 4L divided by 5. So what would be your new frequency? So in your case, you have to compare with the first formation of your stationary wave. So from here to here, you will notice that your wavelength has actually decreased by 5 times. You see, from 4L to 4L over 5, you have actually decreased by 5 times. So therefore, your frequency must increase by 5 times. The frequency that you expect to see here is 5F0. Okay, so frequencies at which stationary waves are formed will be this. You can see the patterns there. Frequencies for stationary wave would therefore be F0, 3F0, 5F0, 7F0, and so on and so forth. Okay, you'll be in odd number multiples of your F0. All right. So from here, how do we go and find out which frequency is not the one? Now, in the first place, let's just consider this. For first stationary wave, for the first stationary wave. Remember, I told you that this one is actually going to be equal to quarter wavelength. So quarter wavelength is equals to L. So quarter wavelength is equals to L. The L is actually given. We know it is 0.85 meters. So let's just sub the value in. So lambda over 4 is equals to 0.85. So lambda is actually going to give us 0.85 times 4. We will get 34 meter here. Okay. And then from there, if you apply equation V is equals to F lambda to find out the frequency for that wavelength, we are already given the speed here. So this one is 340 equals to F times with 34. The frequency is actually going to be 100 hertz. Okay. This frequency is actually our F0. Okay. So in our case, if we go and translate this into what we have above, frequencies for formation of stationary waves, we know the frequencies that we should get would be 100, 300, 500, 700, and so on. So you can actually see 100 here, 300 here, 500 here, but what you could not see is 200. So this is the one that's not possible to give you a stationary wave. All right. So that one is all right. Then now if you move on to question 28, the next one. In question 28, they mentioned that water waves of wavelengths lambda are incident normally on an obstacle with a narrow gap. The width of the gap is equal to wavelength. The waves on the gap emerge over an angle theta as shown here. And then subsequently, they mentioned that the gap is slowly widened. Which changes, if any, will occur to lambda? Sorry, which changes, if any, will occur to theta and to the wavelength of the emerging waves? Okay. So in your case, if you recall for diffraction, there's always this thing that we mentioned. Significant diffraction only occurs. Significant, we would say that significant diffraction occurs when wavelength is comparable to the gap width. Okay. You will only get significant diffraction if your wavelength is comparable to the gap width. So in my case, if the gap width, let's just call the gap width as W and the wavelength as lambda. So if the wavelength, if the gap width is now larger, progressively larger than your wavelength, you will have less diffraction. Okay. If your gap width is slowly widened, it's going to be more than your wavelength now. So you will have less diffraction. So from there, there are two things that you can conclude. If you have less diffraction, you have less theta. Because you see, with the current gap width that you have here, this is your W, your waves were diffracted like this. It is spreading out like this. You just need to look at these lines here. This line here and this line here. Your angle theta is defined according to these two lines. Okay, so this one is if you have significant diffraction. But if you have less diffraction, you probably could look like this. Maybe something like this, as well as something like this. Okay, so this one could be, say, less diffraction. Now look at your angle. Your angle theta is less. Okay, that's why I can say the angle will decrease. Now, what about the wavelength then? Okay, so the wavelength remains unchanged because you did not change anything about the original wave. Okay, because nothing about the original wave was changed. Because rather than saying it original wave, because the incident wave was not changed in any way. Okay, wavelength will be the same before and after passing through the gap. Okay, so wavelength remains constant here. So in our case, which is the correct answer? The answer should be A. Theta decreases, but wavelength remains the same. All right. So that is for question 28. In question 29, light of a single frequency passes through two narrow slits and produces an interference pattern on a screen some distance away. The interference fringes are very close together. Which change here would increase the distance between the fringes? So from reading the question, we know we are talking about a double slit because there is mention of two narrow slits here. So imagine right now that we shine a beam of light onto a double slit, and behind the double slit, there is a screen. So once the light passes through our double slit, it will split apart into a few different beams of light, like this. So that when it hits the screen behind, it will form what you call bright fringes, like this. Okay. So for double slit, there is always one equation that we will always be using. That one being lambda equals to AX over D. Okay. So A refers to the separation between the slits or slit separation. And then X refers to the fringe separation. Okay, specifically the distance between adjacent bright fringes or distance between adjacent dark fringes. And then D refers to the distance between the slit and the screen. Okay, so when they mention right now to increase the distance between the fringes, they are actually talking about the fringe separation X. They want the fringe separation X to increase. Now, from looking at the original equation here, we know that X is equals to lambda D over A. So X will increase if lambda increase, D increase, or A decreases. All right. So let's look at the answer choices one by one here. If we were to increase the brightness of the light source, there's actually no effect on X, no effect on the fringe separation because the brightness of light is actually not represented by the equation here. So if it isn't represented by the equation here, increasing the brightness of light by right should have no effect on the fringe separation. Instead, what will happen is that because we're using a brighter source of light, our bright fringe will be brighter instead. Okay, because the bright fringe is where you have constructed interference. So the waves meeting at a particular bright fringe have larger amplitude now due to larger brightness of your light use. So the resulting wave that you get will be an even brighter spot. Okay, it's an even brighter fringe. And then if you look at B, increase the distance between the slits and the screen. This is actually talking to you about increasing D. So we do not want to increase D, do we? No, we want to increase D actually. So this one is actually correct. All right, A just now was wrong. How about the rest of the answers? If you're talking about increase the distance between the two slits, this is talking to you about increasing A. But do we want to increase A? No, we want to decrease A. So this one is wrong. And then the last one being this. We want to increase the frequency of light use. So how does increasing the frequency of light use actually factor into the equation here? Now, if you recall, B is equals to F lambda, V being constant here would mean that F is inversely proportional to wavelength. So if your frequency increases, your wavelength is dropping. So in our case, this one is actually saying we are using a lower wavelength, but is this what we want? No, we want an increase in wavelength. So this one is also out. So the only answer choice here is B. Okay, so that's for this one. Now then, if you move on to the next question, light of wavelength 5.4 times 10 power minus 7 meter is incident normally on the diffraction grating. The separation between the adjacent lines in the grating is 2 times 10 power 6 meter, and the light that emerges from the grating falls on the semicircular screen as shown in the view from above here. The grating is at the center of the semicircle and the lines of the grating are vertical. How many bright dots are formed on the screen? Okay, so right now, we are not talking about a diffraction grating. Okay, the question before was on the double slit. Now we're talking about a diffraction grating. So what usually happens for a diffraction grating is quite similar to that of a double slit. You shine a beam of light onto a diffraction grating, and then what happens then is that that beam of light that you actually shone onto the diffraction grating will actually split apart into a few beams. It will split apart in a manner similar to this. Okay, where the middle one, the middle beam, which is then incident on the screen, will form a bright dot. That one will be considered as our zero order. And then if you go upwards, this one will be first order, second order, and third order. So the same numbering is repeated for the other side, where this one is first order, second order, and third order. All right. So in our case, for diffraction grating also has a very specific equation that we will use. So let me just erase this and write it at the top instead. Diffraction grating has a very specific equation that we will use, similar to double slit with its own equation. So diffraction grating will use d sine theta equals to n lambda. All right, where d is actually the distance between the slits of your diffraction grating, your n is the order number, and lambda is actually your wavelength. The sine theta here, the theta is the angle of diffraction. Namely, if let's say you're talking about first order, n equals to 1, you want to find the angle theta, that one will actually be this one. Okay, so that's the background of this equation. Now you want to find first the maximum order number. Just now, as I mentioned, when your beam of light is shown through the diffraction grating, you have the beam of light splitting into a few different beams, where it starts from 0 and then gradually increases in terms of the order number. The order number cannot increase indefinitely. It will reach a maximum value. So we are first interested to find out what is our maximum order number in the first place. So in your case, you look at sine theta. Sine theta has a maximum value of 1, and that one will only be achieved when the angle theta is 90. So we can say this, n is max when theta is 90. Okay, because to get n max, we need to have sine theta being maximum. Okay, so sine theta will be maximum at 90 degrees. If you sum in the values now, you will get d sine 90 equals to n lambda, and sine 90 being 1 here, you will eventually get n max equals to d over lambda. Okay, so if you try to find out what is your n max now from the question, your d being the distance between the adjacent slits, or in your case, adjacent lines in the grating, that one is 2 times 10 power minus 6 divided by your wavelength of 5.4 times 10 power minus 7. What will you get? 2 times 10 power minus 6 divided by 5.4 divided by 10 power minus 7. You will eventually get 3.7. Okay. Now, when it comes to finding the maximum order number for diffraction grating, you either take integer value only, or you round down. So therefore, your n max is actually 3. Okay, so this means that when your beam of light is actually shown through the diffraction grating and it splits into different beams, it will only go up to a maximum of 3 beams on either side of your center line. Okay, but here the question isn't really asking you about what's your maximum order number. Instead, they're asking you about how many bright dots are actually formed on the screen. Meaning to say they want to find out how many of the bright dots can you see throughout the screen. So in your case, if you want to find the total bright dots, it is generally 2n max. Sorry, this is 2n max plus 1. Why is it 2n max in the first place? Is because you have 0 going to n max here, and you also have 0 going to n max below. So you actually have twice of the bright dots there. So it is 2 times of n max. And then why is it that you have a plus 1 here? That one is to take into account the bright dots at the center line. Okay. So in your case, if that is already known, what is your n max? You can just sum in the values. 2 times 3 plus 1 gives you 7. So your bright dots on the screen is actually just 7. Okay. Okay, then let me just clear off the screen here and move on to the next specific set of questions. Now, in the next question, this is already on current of electricity. Now, in question 31, you have a straight copper wire of diameter 0.42 times 10 power minus 3 meter that has a number density of free electrons of 8.5 times 10 power 28 meter cube. In a given time interval, a charge of 0.15 coulomb moves through the wire. What will be the average displacement of the free electrons along the wire in this time interval? Okay. Now, since they made mention of number density, the only equation that you've learned so far that relates number density is just this. I is equals to AN QB. Okay. So in your case, you can try to expand this equation a bit further where you say A is actually pi over 4d squared because the A here refers to the circular cross-sectional area of your wire, and then multiply with number density, multiply with Q, and then multiply with L over T. Okay, so it would be better if I just draw a diagram here to let you see what I mean by all these symbols. Consider this being your copper wire, a section of your copper wire. Your cross-sectional area A is actually this, A being pi over 4 d squared. So you have some electrons that are actually moving through your copper wire like this. So in a given time interval t, they would have moved a certain distance. Let's call this distance here L. Okay, maybe I should use a different color. So your distance move here, you can call it as, say, L. All right. All right. The distance L move over a certain time t will give you your velocity. So this one is actually L over t. Okay. Now, they've also made mention of charge here. So how do you relate your equation with charge? Now, if you recall that current is actually defined as rate of flow of charge, you could actually rewrite current here as Q over T. Okay. All right. Now, notice that you have the same term T on both sides. Okay. Now, in your case, you were never given the time interval. They just say a given time interval. So in our case, even if we do not know what is the time interval, it won't be an issue because the T's here will cancel off. So our equation eventually simplifies to Q equals to pi over 4 d squared and QL. The displacement that they're talking about here is actually this L. This is what they want to find. Okay, so if we sum in all our relevant values, we will get 0.15 equals to pi over 4 times d squared of 0.42 times 10 power minus 3 squared, then multiply with your number density of 8.5 times 10 power 28, then multiply with the charge of electron of 1.6 times 10 power minus 19, and then finally L would eventually be 7.96 times 10 power minus 5 meter. This one will actually be answer choice C if you round it up to SF. Okay, so that's for question 31. And then if you look at question 32, what is the definition of potential difference across a component? Okay, so when it comes to potential difference, the formal definition of potential difference was electrical energy converted to other forms of energy per unit charge. And the equation would be V equals to W over Q. Okay, so you look at the specific answer choices that you have here, which one actually closely relates to what is being written here? For A, they mentioned it is the electrical power supplied to the component. PD is voltage. It is not talking about power, so this is out. And then after that, if you look at the next answer choice, we says that it is the energy transferred to the component per unit charge. This one seems to closely relate to this. So this one could be your possible answer. Okay, but let's just check the rest of the answers just to be sure. If you are talking about C, the product of current in the component and its resistance, this is actually just basically saying to you it is V equals to IR. It is just the equation relating PD, current, and resistance together, but it's not how your PD was defined. Okay, no doubt if you go and rearrange this equation, you will get V is equals to IR, but this is not the equation that defines PD. This one actually came from the equation that defined resistance, where resistance is the ratio of PD to current. If you rearrange that, you get V equals to IR. Okay, but this equation by itself does not define PD. It is used to define resistance. The one that is used to define PD is actually this one. Okay, so C is also out. All right. Then after that, if you look at the last one, D is the voltage across the component. Yes, but it's a bit generic. So it could be more detailed. So this one is out because it is generic. Okay, it's just saying, oh, it's voltage. And then for C, how would I revert this? This one is actually equation that defines R, not PD. Okay, so this particular equation is used to define R, not PD, so we cannot use C. So here, obviously B is the only correct answer here. All right, so 32 is B. Then we move on to the next question. Okay, in question 33, the graph shows the IV characteristic of a semiconductor diode. This particular component is a semiconductor diode. So from there, what statement can be deduced from the graph itself? So before we move on into the answer choices, let's just have some background info sorted out. So what is Ohm's law in the first place? Now, Ohm's law states that PD is directly proportional to current, provided temperature remains constant. Okay, so of interest to you is the part where they say PD is directly proportional to current. When they say PD is directly proportional to current, this means that resistance is constant. Okay, Ohm's law saying that PD is directly proportional to current would have actually implied that resistance is constant. Okay, and then from there, what can we then further do? Now, if you're talking about resistance, resistance is defined as the ratio of PD to current. Okay, but if you want to find just the magnitude of the current, we can do something else. But magnitude-wise, resistance is actually equal to the gradient from origin of your IV graph or your VI graph. All right. So magnitude-wise, if you want to find out the resistance of something, it's actually equal to the gradient from origin. So let me just rewrite this properly for you. It's actually equals to the gradient, but measured from origin. Okay. So to give you an idea of what I mean by that, you see that this is an IV graph. So if you have an IV graph, let's just say that in my case, I have an IV graph that looks like this. Okay, I have an IV graph that looks like this. If I say that I have a straight line through origin like this one I can say that in my case, the gradient from origin is actually equals to I over V is actually equals to the reciprocal of my resistance. Okay, so in other words, what I can say here is that gradient is actually inversely proportional to R. Okay, inversely proportional to my resistance over here. All right, so if I have an IV graph that looks like this, notice that my gradient is constant. In my case, this one, I can actually just say that the gradient from origin is constant. Therefore, R is constant. No matter which point I pick, the gradient for the origin always remains the same. That's why I say here the gradient is constant, therefore R is constant. But what about a case where you have a graph that starts to curve? So let's just say right now I have the same IV graph like this, but it starts to curve in a manner similar to this. So let me just draw this. Okay, not this arrow. It starts to curve in a manner that is similar to this. Okay, so it's still an IV graph, but how would I describe its resistance? You see how the gradient from the origin changes, right? So in my case, let's just consider two specific points, or rather three. I have one point here. I have another point here. And then I have one point here. So try to look at the gradient or from the origin to those specific points. For the pink colored point, it was this. For the orange colored point, it was this. And then for the blue colored point, it is this. So in my case, because I know that gradient from origin is inversely proportional to R, you can actually see that as I go from point number 1 to point number 2 to point number 3, my gradient is actually decreasing. So therefore, my resistance is increasing. Okay, so this is how I would look at how my resistance varies from a IV graph. All right, so that one is all right. Okay, then from here, let's look at our specific answer choices. If you look at answer choice A, where they say above a certain positive potential difference, the diode obeys Ohm's law. So your positive potential difference is going from here to here. This is where you have your positive potential difference. So they say that your diode obeys Ohm's law now. So remember just now I told you Ohm's law implies that your resistance is going to be constant. So if you look at the graph for positive potential difference being this part alone, can I say that the resistance is actually constant? Now let's just consider what we just did before. If I consider just 2 points here, 1 point here, and then another point right over here, do I see that the gradient from origin is constant here? You don't, right? You see this one, the pink colored line and the black colored line, you can actually see that in your case, the gradient is actually increasing. Therefore, your resistance is dropping because gradient from origin here, from an IV graph, the gradient is inversely proportional to resistance. Okay, so here, this one is definitely out because R is not constant. If it obeys Ohm's law, it must be constant resistance in the first place. All right. Then if you look at answer choice B, the current is directly proportional to potential difference when the current in the diode is in one direction. So take note of the wording that they use here. They say current is directly proportional to potential difference. Okay. So when they say current is directly proportional to potential difference, it means something like this. If I is directly proportional to potential difference, if you were to plot an IV graph, because we say that current is directly proportional to potential difference, it should actually give you a straight line graph through the origin. Okay, but look at your current graph right now. Do you get any straight line graph through origin? You don't see any, do you? The one on the right hand side here is a curved line. The one on the left hand side here is also kind of like a curved line. All right, so there's no straight line through origin here. So this one is also out. Okay, so this one is out because no straight line through the origin. So this one is out. Now then you look at C, the diode has zero resistance when the current in the diode is in one direction. So let's have a look at the part where they tell you zero resistance. Okay, so let me just rewrite certain things here. This one is actually part 3. Okay, for part 4, let's have a look at it like this. Now, we know that resistance is defined as the ratio of PD to current. Let's just say what happens when you rearrange this so that current is now V over R. Now, if R is 0, this would tell you current is infinite. Okay, current is infinite. Because when you divide something by 0, you should get infinite. Okay, so here R equals to 0, I is equals to infinite, which would make sense. If you have no resistance whatsoever, your current can theoretically go up to an infinite value. There's no limit to it. Okay. So in our case here, the current should be almost vertical if we have infinite current. Now, if you just look at the graph that you have in the question right now, on the left-hand side, you don't see any part of the graph being almost vertical. Neither do you see on the right-hand side where the graph is almost vertical. When we say the graph is almost vertical, so that your current is infinite, it actually would look something similar to this. Let me just find a suitable color to use. Okay, I'll just use blue color. It will look something like this. So when you see a graph that looks like this, this is your current being almost vertical on the graph. This will imply to you current is actually infinite. Okay, so you don't see in your graph right now, so answer C is actually wrong. Okay, the diode has zero resistance when the current in the diode is in one direction. So this is out. So the last one should be the correct answer here. But let's check that one out too. The resistance of the diode depends upon the potential difference across it. So in your case, if you look at how the resistance changes with potential difference, we actually did something related to this earlier in part 1. Remember just now when we wanted to see whether the diode in part A obeys Ohm's law, we actually evaluated the resistance where we plotted this first point here and look at the gradient from origin, and then we plotted this second point here and look at the gradient from origin. We noticed that the gradient from origin was changing Specifically, it was increasing so that the resistance is dropping. So in your case, them saying that the resistance of the diode depends upon the potential difference across it, this is actually correct. Because you can see when your PD change, your gradient from origin change, therefore your resistance changes. So the answer here is D. All right. Okay, so that one is all right. Then we move on to question 34. For question 34, you have a wire of resistance 30 ohm. A second wire is made of the same material, has the same mass, and is 3 times as long as the first wire. What is the resistance of the second wire? Now, when you see that there's mention of length and resistance here, you already should know by now that you are going to use this equation. R is rho L over A. Now, they told you that you are making the wires out of the same material, so this means you have same resistivity. So in your case, looking at the first equation, rho is constant. That will mean that R is proportional to L over A. So you can find mention of the length, but you cannot find mention about the area inside your question. They never make mention anything about the area, neither did they make mention anything about the diameter. So you have to use something else to find out what's happening to the area now. So notice that they make mention of mass and also length after that. The next equation that you want to use is actually the equation for density, where we say density is mass per unit volume, okay? So you imagine the wire right now being something like this with a circular cross-sectional area. Your cross-sectional area A is this. Your length L is this. Your equation for density can be further re-expressed as M over AL, okay? So now you have two different density symbols. Don't confuse one for the other. This one is resistivity. This one is density, okay? Now, when the question mentioned that you are making the wires out of the same material, not only does it mean you have same resistivity, it also means you have same density. So in your case, you could have actually said that rho and M constant here, therefore, A is actually inversely proportional to length. So in your case, you can actually say this now. For your second wire, since the length is 3 times as long as the original, as the first wire, your area is actually 3 times as small, okay? So this is the relation between your length and your area right now. Now you can move back to your first equation. So if you try to analyze the effects of L and A individually on R, you ought to be getting something like this. If L increased by 3 times, I'm still talking about second wire, right? For second wire, if L increased by 3 times, by right, the resistance ought to increase by 3 times. But if, say, your area, you already found out in equation 2 here, that area is reduced by 3 times, your resistance ought to increase by 3 times too, okay? So from here, what can you then say? Overall, your R would have increased by 9 times. So therefore, R2 is actually 9 times of R1, where you take 9 times the resistance R1, which is 30 ohms here, you will get 270 ohms as your final answer. The answer is D, okay? So that's for this one. Now in question 35, a cell has internal resistance R and electromotive force E. The cell is connected in series with an ammeter and a variable resistor of resistance R. Then they mentioned to you this, when R is 10 ohms, the ammeter reading is 0.3 amps. When R is 5 ohms, the ammeter reads 0.4 amps. What is the value E? What is the value of your EMF here? Okay, so to do this particular question, let's just apply Kirchhoff's second law in the first place. So if you apply Kirchhoff's second law for this loop here, K2 law will tell you this. K2 law will tell you that your E is equals to the PD across your variable resistor plus the PD across your internal resistance. From there, you can then further expand this to become I times big R plus small r. Okay, you are going to have the same current flowing throughout the entire circuit because your components are all connected in series here. All right. Okay, so in your case, let's consider the individual situations that has been described here. In the first instance, they say that when R is equals to 10 ohms, I is 0.3 amps. So you will get this. E equals to 0.3 times with 10 plus with small r. This one, let's call this equation 1. And then when you look at the second situation that has been described to you, where they say when R is equals to 5 ohms, current is actually 0.4 amps. So the original equation from Kirchhoff's second law was this. You just sub in your values. E is equals to 0.4 times with 5 plus R. So this is equation 2. Okay. So by right, your EMF E for both cases should be the same. Okay. You did not change out the battery. So you can actually equate 1 and 2 together. So in your case, if you equate 1 and 2 together, you will get 0.310 plus R equals to 0.4 5 plus R. So eventually you will get 0.75 10 plus R equals to 5 plus R. Okay, this is the equation you are going to get. And then after that, you simplify this, what you will get is 7.5 plus 0.75 R equals to 5 plus R. So further simplify this, you will get R as 10 ohms. Okay, so from here, you can actually now find out what is E. You can either make use of equation 1 here or equation 2 here. All right, both equations have two unknowns, but you've now since found small r here, the internal resistance, from which you can now find out what is your EMF. All right, so you can just pick either one. You can just say from equation 1, E is actually equals to 0.3 times with 10 plus with 10, giving you the final answer as 6 volts. So answer is D. All right. For question 36, the sum of currents entering a junction in an electrical circuit is always equal to the sum of currents leaving the junction. Why is this? This is actually referring to Kirchhoff's first law, which basically says that the sum of currents going into a junction is equal to the sum of currents going out of a junction. So let's just say, for example, we have a junction here, and there are a few paths that feed into this junction. So you have one path here, another one here, and another one here, followed by two others that feed outwards, like this and like this. So if I say that on the left-hand side, you have current I1, current I2, and current I3 feeding into this junction, and then after that, I have current I4 and I5 that's going out of the junction. According to Kirchhoff's first law, I can say that I1 plus I2 plus I3 will be equals to I4 plus I5. Now, if I look at the current in terms of charge per unit time, I will get this Q1 over T plus Q2 over T plus Q3 over T equals to Q4 over T plus Q5 over T. So you can see that in your case, the sum of charges in is equals to the sum of charges out. So this is actually conservation of charge. Because in your case, if you say that there are 100 electrons going in to this junction here, you will have the same 100 electrons going out the same junction. Okay, so that's Kirchhoff's first law. So in your case, why is this so? Why is that current going into a junction is equal to current out of a junction is actually a consequence of conservation of charge. All right. The rest of the answer saying is a consequence of the conservation of EMF, is a consequence of conservation of energy, is a consequence of conservation of potential difference. Those are not relevant. Now, specifically, if you're talking about conservation of energy, this is actually related to Kirchhoff's second law. So if you try to relate to Kirchhoff's second law, Kirchhoff's second law tells you this: sum of EMF equals to sum of PD. So for example, if I have a circuit that looks like this right now, with one cell and 3 resistors there, I can say that this one is EMF E, this one has PD V1, PD V2, and PD V3. According to Kirchhoff's second law, this would actually be E equals to V1 plus V2 plus V3. Now, if I look at this in terms of energy per unit charge, which is actually the definition of voltage, you actually get this: W E over Q is equals to W1 over Q plus W2 over Q plus W3 over Q. So in your case, you then say that this one, electrical energy gain is equals to electrical energy loss. So this one would actually be a consequence of conservation of energy. If you gain 100 joules of electrical energy here at the battery, you will lose a total of 100 joules of energy, 100 joules of electrical energy at the resistors here. Okay, so that is question 36. For question 37, in the circuit shown, the temperature remains constant. In which circuit does the potential difference V increase with increasing light intensity? Now, if you look closer at the circuits, there is a thermistor and an LDR. These are resistors whose resistance tend to change. So if you just look at for a thermistor, whose symbol is just like this, what we will say is that if you look at the variation of thermistor resistance with temperature, the graph looks like this. Okay, this one tells you this: when temperature increases, resistance of thermistor drops. When temperature decreases, resistance of thermistor increases. And then if let's just say you have a case where temperature is constant, like what the question mentioned, the resistance of your thermistor should be constant too. Okay, they already mentioned to you here that the temperature remains constant. So the resistance of your thermistor in your circuits shown should be constant. Now, if you then move on to an LDR is something that looks like this with the arrows pointing towards it. If you look at the variation of the LDR resistance with intensity of light, you should get something like this. Let's just call this intensity, which is also brightness of light. You will get the same graph shape as that of the thermistor. So in your case, you would say when intensity increase, resistance of LDR drops. When intensity drops, resistance of LDR increases. Okay, so that's what you can actually say for the thermistor as well as the LDR. Okay, next, if you look at each of the circuits shown, current flow will only be within these loops that are highlighted here. That's because all your components are connected in series. There are no parallel connections here. So you look at the current, it will all be somewhat similar to this. Okay, so let's give me some time to draw them out. So this is your current flow through each of the circuit right now. Now from here, you can actually draw one conclusion. For each respective circuit, the same current flows through all the resistors. Okay, you have same current flowing through all the resistors, meaning to say if you look at answer choice A, the same current flows through these two resistors. Answer choice B, the same current also flows through these two resistors. That's what I meant by that. So you then apply V equals to IR for those two resistors in each circuit. You will get something like this. V is equals to IR. Since I is constant through all the resistors, that would mean that the PD across them is directly proportional to their resistance. So from here, you can actually say that when your R increases, your PD increases, and vice versa. Okay, so that is one part here. Okay, next comes the part where you want to apply Kirchhoff's second law. So if you apply Kirchhoff's second law already tells you this, where sum of EMF is equals to sum of PD, isn't it? So you apply for each of the respective circuits shown here, we would expect to see expressions like this. EMF E for circuit A is equals to the PD across your thermistor plus the PD across your fixed resistor. And then for circuit B, EMF E is equals to the voltage across your LDR plus the voltage across the fixed resistor. For circuit C, EMF E is equals to the voltage across your LDR plus voltage across your thermistor. And lastly, for circuit D, EMF E is equals to the voltage across your thermistor plus voltage across your LDR. Okay, so let me just write this properly. This is plus P LDR. Okay, now notice that there's actually two I's in the writings on the screen right now. This I here is actually referring to current, whereas this I here is actually referring to light intensity. Okay, so in order to avoid any kind of confusion going forward, I'll just refer to the light intensity directly as something else. So let's just say, for example, I call this brightness. Brightness increase, because the question here wants voltage measurement that increases with light intensity. So if my brightness increase, what do you suppose will happen to my thermistor and my fixed resistor? The resistance on my thermistor and fixed resistor is actually unchanged. They are not affected by light intensity. So in my case, I will actually say this: VT and VR remain unchanged. So in my case, the voltage measurement here is actually no change, because this voltage measurement is actually measuring directly the voltage across my thermistor. Then if you move on to circuit B, what happens when my brightness increase? So when your brightness increases here, the resistance of your LDR would actually decrease. So the voltage across your LDR would drop. So in your case now, your EMF value, maybe I should use a different color, just give me a moment. In your case here, if you apply Kirchhoff's second law, your EMF value is actually fixed. Okay, it doesn't change, but your voltage of your LDR has dropped. So in return, the voltage across your fixed resistor must increase in order for your EMF to remain the same. Okay, now your V here is actually measuring the voltage across your LDR. This is your V. So this one is actually decreasing. Your voltage value is actually decreasing. This is not what you want. Okay, A is out, B is out. So let's have a look at C then. what happens when your brightness increase? So same thing as before, when brightness increase, the resistance of my LDR would drop such that the voltage across my LDR would drop. So same thing, EMF E remains fixed, voltage across LDR drops, but voltage across my thermistor would increase. Okay, so in my case now, your voltage is actually measured across your thermistor. Sorry, this is not your thermistor. Your voltage is actually measured across your LDR. So this one is again your V. So it's actually decreasing. This is not what you want either. Okay. Then the last one ought to be the correct one, but let's double check. If your brightness is increasing, same thing as before, your resistance of your LDR drops, your voltage across your LDR drops. So your EMF E being fixed here, your voltage across LDR drops, your voltage across your thermistor increases. So right now, if you look at where your voltage is actually measured, it's actually measured across your thermistor. So this one here is actually your V. So your V here is actually increasing. This is what you want. The answer is D. Okay. So that is for this one. Then I'll move on to the next one. All right, for the last page of your paper, question 38, carbon-14 decays into nitrogen-14 by emitting a beta-minus particle. Which statement explains why the beta-minus particles are emitted with a range of different kinetic energies? Okay, so let's just try to first write out the equation for the reaction that occurs here. We just write it in a simple manner. Let's just say that carbon-14 right now decays into nitrogen-14 by emitting a beta-minus particle and is anti-neutrino. Okay, we already know that whenever you have beta-minus decay, it will be neutron changing to a proton, giving you your beta-minus particle and your electron anti-neutrino. Okay, so in your case, when your carbon-14 decays to become nitrogen-14 by emitting beta-minus particle along, there should be an electron anti-neutrino along with it. Because what you will learn in particle physics is that your electron will always be emitted with its neutrino. Okay, so right now, when you're talking about the energy release as a result of this reaction, your energy release will actually be shared between these three particles, and they will be shared by unequal amounts each time. They will be shared by random amounts each time. So in your case, that kind of explains to you why your beta-minus particle always have different kinetic energies. It's because the energy released in your decay process is shared between the nitrogen-14 nucleus, a beta-minus particle, and an anti-neutrino. Okay, so that is question 38. Then we move on to question 39. A nucleus of radioactive element emits an alpha particle, then a beta-minus particle, then another beta-minus particle. Which statement here describes the final element that is to be produced? So if you read the question right now, there's actually two beta-minus particle emitted and one alpha particle that's emitted. So to make your life simple, let's just write an equation to represent the decay. So in our case, let's consider an element X with nucleon number A and proton number Z. So this will then decay into another unknown element whose nucleon number is A prime and proton number is Z prime. So in your case, you have two beta-minus particle emitted. Let me just rewrite this properly. You have two beta-minus particle emitted and one alpha particle emitted. So you know that in any kind of nuclear reaction, or any nuclear reaction which includes decay, there's always conservation of proton number and nucleon number. We know that proton number before the reaction will be equals to the proton number after the reaction. And then likewise, when you're talking about the nucleon number before the reaction, it will be equal to the nucleon number after the reaction. Okay, so we try to make use of these conservation laws. Let's just look at proton number first. Okay, I'll just write on the top right-hand corner. If you're looking at the proton number alone, you will say that Z is equals to Z prime plus with -2 plus with 2. So in your case, Z prime is actually just Z. What you can say from here is there's no change in proton number. Okay. Now you move on to nucleon number. Let's have a look at what happens to your nucleon number. So in your case, nucleon number is A equals to A prime plus 0 plus 4. Okay. So in your case, A prime is actually A minus 4. So what can you actually say from here? We can actually say that the nucleon number has actually decreased by 4. Okay. So they want you to find out what is the final element that is produced. This element Y that I just wrote here is actually the final element that we're trying to find out. So what can you comment about this final element is this. We can see that the final element has the same proton number. It has same proton number, but different nucleon number. So when we have same proton number but different nucleon number, we already should know that this one is going to be an isotope. Therefore, is an isotope. The answer ought to have been C here. It is an isotope of the original element. But let's check against the other answers just to be sure. Now in A, they mention it's a different element of higher proton number than the original element. So what is wrong here is them saying you have higher proton number. We already know there's no change in proton number. So this is wrong. And then if you look at B, they mention is a different element of lower nucleon number than the original element. Now, them saying that your nucleon number is lower is correct because you can see that the nucleon number decreased by 4. But what is the thing that made this answer wrong is the fact that they say it's a different element. Okay, so when you have no change in proton number, this means is the same element. Okay, it is the same element. Okay, so let me just write another statement here. Different proton number produces different element. Okay, so in our case, as the proton number did not change, it would still be the same element. Okay, so what's wrong here is them saying it was a different element in the first place. It should be same element. Okay, then you look at the last answer choice D. They say that it's the same element as the original element, but with a different proton number. So the only thing that's wrong here is them saying it's a different proton number. We already know that your proton number is unchanged. Okay. All right, then we move on to the last question for this paper. Now, how many hadrons, baryons, and mesons are there in the nucleus of beryllium-94? So let's just review a little what is hadron, meson, and baryon. Now, when we talk about a hadron, we know a hadron is just group of quarks. And then when you're talking about hadrons, there are more specific classifications for groups of quarks. The first one being meson. Okay. Meson is actually just a pair of quark and anti-quark. And then the next one is your baryon. Okay. Now your baryon is just a group of 3 quarks. Okay. Now, when you're talking about neutrons and protons are actually both hadrons and baryons. So neutrons and protons are both hadrons and baryons. Okay, they are both hadrons and baryons because you know that the quark composition of a neutron is actually up, down, down, whereas the quark composition for a proton is up, up, down. So their group of quarks, they are hadrons. Their group of 3 quarks, they are baryons. Okay, so now to answer this question, how many hadrons, baryons, and mesons are there in beryllium 94? Let's have a look at the nuclide notation. So let's separate out the question here. If you're talking about beryllium 94, this should tell you that you actually have 4 protons because the proton number is 4, and you should have 5 neutrons. If you take the nucleon number minus the proton number, you should get the number of neutrons. So in your case, you have 4 protons and 5 neutrons. This should tell you that you have 9 hadrons as well as 9 baryons. So your answer should be C. Okay? So this is the last question for this paper. We are done with it.